In this video, we'll take a short look at the automorphism groups of complete graphs. So, yeah, this is the question. What is the automorphism group of Kn for n greater than or equal to 3? So let's maybe start with just K3. And how about I label it U, V, and W. And we'll think about what are all of the automorphisms here. So let's see, I can go sort of vertex by vertex. I can say, okay, where can I send U? So there's three sort of options for U. I could either send U to U, I could send U to V, or I could possibly send U to W. Now, as we've done before, it's possible that these don't turn into any automorphisms, that just picking where I send U maybe doesn't lead to an actual automorphism. Maybe it's not possible to preserve edges by doing that, but this is certainly a way to start for any automorphism. So let's see, what if I send U to U? Well, then I need to preserve edges. I need to preserve this edge UV, and I need to preserve the edge UW as well as the edge VW. So I actually have two options now coming off of sending U to U. Either I leave V fixed, so now I'll send V to V, or I swap V and W, and V goes to W here. So if I send V to V, well, in order to preserve the edge UW, I need to send W to W, or actually, really, that's just, in order for this to be a bijection, I need to send W to W. And so that gives me one, that's a poor way to think about it. Let me circle the whole thing. So this gives me one automorphism. Of course, that's the identity automorphism. So if I send V to W, necessarily then I have to send W to V. Again, that's my only. And this gives me a permutation or an automorphism. So this is leaving U fixed. I'm not going to label this one right now. So let's see. What if I send U to V? So U goes to V. So I could think of this like it looks like I'm rotating counterclockwise here. So I could send V to W. V goes to W. Or I could send, let's see, if I send U to V, I could send V to U and then leave W fixed. That would also preserve edges. So how about I also do V gets sent to U? So in the case I send V to W, that means I have to send, that means W has to be, right? So wait, I said U to V, V to W, and then W would have to be sent to U. So this corresponds to a rotation. I send V to U and U to V, then W has to remain fixed. So there's one. And now let's see, what if I send U to W? Well, this looks like a rotation in the other direction. So if I send U to W, it's possible I could send W back to U and then keep V fixed. Or I could send W to V and do this like a rotation. W to V and then V to U. And that also gives me an automorphism. So here's it looks like I have 6 automorphisms that came off of this. And I'm going to label each one of these with its cycle presentation. So this one's the identity. Can't really give a cycle presentation for that one. But here I'm sending U to U. I'm swapping V and W in this one. So my automorphism would look like VW. Right, V to W, W back to V. Let's see, UV, VW, WU, that's a cycle. That's U, V, W. Here I'm swapping U and V and leaving W fixed. So that's that one. So maybe I'll call these, I don't know, how about alpha 1, alpha 2, alpha 3. Here equals alpha 4 here. Let's see, I'm sending U to W and W to U. I'm swapping U and W. And let's see, U, W, WV, that's this other cycle. So U to W and W to V, and then V back to U. So I'll call that one alpha 5. And so it looks like we have 6 So the order of the automorphism group of K3 is 6. And so, yeah, you may or may not have had some group theory courses. Do you recognize this group? One thing to notice here is that if I list so look at my vertex set of G, it's U, V, W. My cycle presentations here are every possible permutation of these 3 labels, or of these 3 vertices. So this is all possible permutations and by permutation here I mean a bijection from UVW back to itself, right? That is, this gave me every possible way to rearrange the vertices in the graph are present here. And so what this group is, automorphism of K3, well, there's a special group that we call this, that's the group of permutations of a n element set, that's Sn. So this is S3, and this is called the symmetric group. Symmetric group of order 3. In general, right, it's not too hard to see. We just have to preserve adjacency, but any 2 vertices are adjacent. And so it doesn't matter how I pick my permutation of my vertex set, it'll always lead to an automorphism. Right? If everything's adjacent, I don't have to worry at all about where I send my vertices. I can pick any permutation at all. And so in general, the automorphism group of Kn is Sn. And that's the symmetric group of order n. And in fact, we can say a little bit more. We can say, we'll see this in a later theorem, that if G is a graph such that the automorphism group of G is equal to Sn, this is true if and only if G is Kn. That indeed, Kn or the empty graph, the complement of Kn. So we'll see this in a second, but we can actually say a little bit more here, that the complete graph, right, where any 2 vertices are adjacent, we don't have to worry about preserving adjacency because it's automatically preserved, or the empty graph, where again, we don't have to worry about adjacency or non-adjacency because any 2 vertices are non-adjacent. So both of these have symmetric group as their automorphism group. All right, in the next video, we'll take a look at some facts and theorems about automorphism groups. I'll see you there.